All right, so welcome everyone to the second session of HATRA today. Lovely to see a full room, and we have a number of people joining us online as well. So we'll mix that in hybrid mode. But our first talk today is exploring the verifiability of code generated by GitHub Copilot, and by Dakota Wong, Austin Kopig, and Patrick Lamb. And Patrick will give the talk.
Thanks, Jonathan. Kilo Kutu is what they say here, so I can pretend to be a new one. All right, and this is work done by grad students Dakota and Austin, and they couldn't make it here, so I guess I'm the last guy standing, and here I am. If you want to follow the talk, I guess the screen is pretty small and you can see it. We're pretty big, but it's on my webpage as well, and so you can actually click on that link and follow on your computer. All right, so how did we get here? So, unless you've been living under a rock, GitHub Copilot has been a thing. I will say what it does, but everyone's been talking about it. Like, educators have been like, oh no, students are going to use it to like write programs for their assignments, and then like ChatGPT is like, oh no, people are going to use it to do like essay problems. Anyway, this is 2022, I guess. And so it's your AI pair programmer, and so their saying is, trained on billions of lines of code, GitHub Copilot turns natural language prompts into coding suggestions across dozens of languages. And so we're going to look into this a bit more. And so let's talk about what it does in particular. So what we do here is I, as a user of Copilot, say, define binary search, array list, target int, and it returns an int. Actually a Boolean, but an int. And so I set to Python, and I say, go Copilot. And then Copilot is like, okay, fine. Here is a binary search implementation. And so this is, Dakota and Austin tell me, this is what Copilot generated. All right, so what we're interested in is it possible to formally verify Copilot generated code? And so that's our goal. All these pictures, sometimes I kind of stumble, but yeah. That's the goal. Northwest Territories, friendly. And so let's talk a bit about what other people have done in the past, in the recent past, because Copilot was a thing this year. And so other people have done a lot of things on Copilot this year. And so Marie and Maggie this year asked the question, does Copilot generated code pass tests? And I'm pretty careful with my words here, right? So I said, my goal is to see whether Copilot code verifies. Their goal is to see whether it passes tests or not. And so in their approach, they evaluate it using leak code questions. So this comes with Oracle, and you can run the generated code on the tests. And so they did it for 4 languages, and what I'm reporting here from their work is for Java, it solves 19 of the 33 problems. And so solve, do you really believe input output? It's pretty good, I guess, but certainly I remember when I was doing programming contests, sometimes I submitted things that were kind of sketchy, but it passed the input output tests. Like, well, maybe it's right. But what we want to know is, does it verify? And that's a different question than does it pass the tests or not. They also had some comments about it, like the code that was generated was not clean, and what they meant by that was the imports weren't quite right. Sometimes they forgot some imports, and it's just kind of not the code that you would really like to write. So again, so they're like, does the code pass tests? And so very often it does, and we're like, is the code verifiable? And there's been other work this year, Copilot versus genetic programming on program synthesis benchmarks. And so I did, they didn't, again, so what does correct mean, right? So I went and looked at the paper where the program synthesis benchmarks were proposed, and as far as I can tell, they have like, for the program synthesis, they have training data and they have test data, and so correct means that it passes on test data. Right? So that Copilot generated the correct solution on 24 of the 29 benchmarks that they did, and genetic programming 25. So they're like, yeah, pretty close. They point out that the difference between Copilot and GP is that GP needs label data, and it's hard to get this. Some person has to go and look at all the source data and create the training and test data. Copilot knowledge just ingest like hunks of code. It's like, here's your code, and just pass it through the language model, and then it generates code based on that. And again, generated code, Copilot and GP both generated hard to understand code. The conclusion of Sobadia, Brace, and Rothloff was that Copilot actually often generated better code than GP. The code that GP generated was more bloated and hard to understand than the code that Copilot did. Still not perfect, but better. So I'm gonna finish talking about related work on this side. And so,
Yeah. Does this mean we can say that the sort of first year programming problems that you find in leak code are actually much more difficult than the problems that the AI people generally tackle?
about the same, eh?
Because it didn't do as well on the leak code as it did on this.
I guess what I would say is that it's kind of, it's like also like how well you specify it, right? And so I think the leak code, all it had to work with was just a signature. And yeah, I would, in the end, I'm not actually that interested in implementing binary search either, right? So that's another question, which is totally orthogonal to what we're talking about here. Right, so the other things are, there's about how people use Copilot. So Copilot versus humans, and then Copilot with humans. And so their conclusion was, can be used for early stage prototyping and Copilot user study. And so like, I guess we hate blank slates, right? It's like you try to write a talk and you have nothing. It's like, oh no, this sucks. And so it's like you get this code, you get this pile of code from Copilot, and you start from there. Maybe you finish there, and maybe that's not so great. But you have something to work with, and you ideally would use that as something that you work with to make the code that you actually want. Right? So we're seeing these things a lot as well. It's the kind of the garbage in, garbage out thing. And it's also the thing where AI generates decisions that are ethically problematic, right? And in this case, it's technically problematic in that, well, you train it on code that has vulnerabilities. Well, what do you think you're going to get? You're going to get vulnerabilities, right? And code smells, right? So just because it comes from an AI, or exactly because it comes from an AI, means that it's more subject to, or it's just as subject as people to doing these bad things in code, generating vulnerabilities in the code and generating code smells. All right, so enough about other people. Let's make it all about me or about grad students. And so this is what we did in particular. So we have a grad student generated problem description, right? So we picked 6 problems that we wanted to solve. And then we asked Copilot to generate some Python solutions because it didn't generate Dafny when they tried to do it. And then using the famous grad student algorithm, they converted the Python solutions into Dafny code. Also invoking the grad student algorithm, they came up with requires and ensures clauses and tried to verify it using Dafny. I guess we were talking about this yesterday. This is the official Dafny proposal. And they had invariants, and the students came up with the invariants, and then together they came up with either a Dafny agrees, yes, this you verify this code, or no. And so we're going to talk about 2 cases where Dafny does successfully verify, or the students manage to get Dafny to verify, and 2 cases where it does not. Right. So yeah, 6 problems, one of which was one of the problems that Wing and Natty did, and 5 that weren't. And so what we give Copilot is a function signature. So I've showed you one before. Here's another example of one. So I guess the key information here is really the keyword prime factors. This is, if we think about this, is what it's gonna use as a primary input. And then there's also the types. So the types of the parameters and the names of the parameters. Names are a thing as well. And then a return type here. So yeah, descriptor function name, parameter names, parameter types, and output type. And so these are all the inputs that we gave to Copilot, right? So we had binary search, then we had the 2 sums, leak code problem, largest sum, sort array, prime factors, and max simplify. And so we did the first 4 and not the last 2. All right, so what else did we have to feed? So we had to if it requires the insurance clauses, if you want to verify, you have to know what you're verifying to. Yeah.
What kind of type should have? I thought my types, the list also included its like member type.
We do not have list member types for Python here. Yeah.
Okay. Is it for a different type checker than my type?
Say again?
Is it for a different Python type checker from the standard one?
I have no clue. I can't answer that question. Sorry. Yeah. Probably for Copilot, it doesn't make a difference. It's like Copilot probably doesn't care. Copilot probably has enough code in the corpus that looks like this, that it's like, I'm just going to generate code that looks like this.
Sure. I guess like list event is probably a little more informative of like, what kind of list you're trying to generate.
But I guess if we're thinking about it, it wouldn't really type check. Anyway, if you said list of it, then it tried to work on list of, or if you didn't say, if you said this, and it's not going to return a float, right? It's
Sure. We can turn a list into something else.
yeah. So requires, ensures, loop invariants are the thing that are hard when you're doing Dafny. And then we added extra requires and ensures clauses as needed during verification. And the requires and ensures clauses that we show are going to use extra predicates. And so we provided those as well. And so this is the results. So we have, the thing about verification, right, is you have this is the number of lines of code you generate. And then look, you have this number of lines of code in the specification. And look, you have this number of lines, this number of invariants. This is the usual story, right? Maybe we kind of made up the difficulty, and by definition, hard is one that we didn't manage to. But no, I mean, we'll talk about that. Okay, so let's talk about binary search. So Austin and Dakota provided these predicates, right? So these are predicates sorted and distinct, which you read the problem description, and we've taken first year computer science, right? We know binary search, and so it has to definitely take a sorted thing. We also require distinct, and then it returns basically a Boolean flag, which is like if it's not one, then it was found. If it was one, it was not found. I can't actually say what order they did. I don't know if they looked at the code first and then came up with this, or if they did the other way around. I guess they would look at the code and then come up with the thing. Okay, so in this case, once you have the requires and ensures, you also need the loop invariants. So they wrote loop invariants. And so basically, there's no magic bullet, right? You have to know the domain, and you're like, okay, I know binary search. Okay, so this is the invariant I need for binary search, right? And so that is an interesting question. It's like, when you don't manage to prove it, is it like, I'm not smart enough? Am I the problem? Or is it that it was wrong? Right? So we don't see that here, but we'll talk about that. But Dafny does verify this one. So it's like, okay, this is good. Copilot generates the thing that we can verify. Yes?
Good question. So you have second line mark. Dafny knows that Python has no integer overflow, right?
Dafny knows that Python has no integer.
Because that would be like a buggy program in C, but not a buggy program in Python.
Well, it's the graduate who knows it, right? Because the graduate knows it, because they're translating, graduates doing the translation.
Yeah, so it generates Python, we convert to Dafny, and then the Dafny thing is verified by Dafny.
Okay.
Yeah.
That's it.
Dave has probably worked much more with Dafny than I have. I'm just a messenger here. So we also did two sums, and actually, what was it? Anyway, types. Yeah, we do have types on this one for read code. So it is listed in. And so, again, we use domain knowledge to come up with these requires and ensures. And lead code does tell you that a valid answer always exists on the input. And so we actually encode that into our requires. Yeah. So then 5 lines of generated Python into 8 lines of Dafny. Like it has no for loops. We make for loops, or we make while loops from easy. Like any undergrad can do that, right? Well, no, let's not talk about undergrads. Many of our brilliant and wise undergrads do that. We wrote 7 invariants, 3 in the outer loop, and 4 in the inner loop, and then verification succeeds. All right, so there's 2 more. I don't have infinite time, I won't show them. If you look at the verification, if you look at the replication package, which I've linked at the end of the presentation, you can look at these as well. So they go through. Fine. So let's talk about cases where this does not go through. And so we have prime factors. What is it? Look at the time. Okay. So we have prime factors, and we, of course, Copilot will say all sorts. You can give it anything, and it'll say something, right? So it says something. And so it looks reasonable. And if I were marking this and I wasn't trying too hard, I would probably mark this correct. Is it actually correct? I'm not sure. Probably correct. So yeah, I guess I was talking last night, and it actually does do the thing where it goes to the square root. And it's actually kind of hard to, we found an external implementation of square root, which was implemented and verified in Dafny. So we used that as a black box, the thing, Python loops. And we also needed a dynamic array, which Dafny doesn't have. So we used a sequence of integers that can't be empty. So we initialized the multiplicative unit. Okay, so what happens? What happens is timeouts, right? And so you go look on the internet about using Dafny, and people are like, yeah, Dafny just times out. It just does. This is a thing that I think, it's like maybe you have better invariants and it doesn't time out, so it's hard to tell whether your invariants are wrong or whether it's just too hard, right? And so we tried to even like force it through, and it just didn't go through, even if you tell it, assume false, it's like, no, still can't do it. So yeah, Dafny timeouts are an issue. And so again, it's like, is it actually incorrect? We don't know. I'm not going to say it's incorrect. I'm going to say this one is probably correct, but we didn't have the time in the context of the course project that it was to verify this. The next one is also even more interesting. And so it's like, I guess we thought it'd be easier than it was. So turn an array into a max heap. And there is a formal specification, which is a appropriate specification for this. And so you have an implementation. And so, yeah, we just provided the first line, and Copilot, like, here, have an implementation. It is recursive, but, and something we were kind of counting on, which didn't happen, was that often max heap apply implementations are going to be like, the recursive call is going to be on a smaller subset of the array. And that's not what happens here, right? So it's actually O(n) squared. And so I guess if I was marking this, I would not give it full marks because it's inefficient. It's n squared instead of n log n. Is it correct? I don't know. So yeah, so it does not obviously reduce the subproblems. And we couldn't make it fail. But does that mean it's correct? No, obviously not. And, the trace tree goes deep. And it's like, yeah, we don't know. And so is it correct? But in fact, not only correctness, but we couldn't prove termination using that. So we didn't even get there. So yeah, I don't know. Someone found in the literature a report of verifying max heapify, and it's, a bachelor's thesis or a master's thesis or something. It's like this document which takes 70 pages verifying max heapify. So maybe it's like, 2 students on a course project couldn't verify max heapify. That's fine. So I think for the previous case, hard is maybe we're the problem, but here I think it's like, legit that it's hard. Yeah.
Do students not verify things on paper anymore? I mean, that's what we used to.
So this was in the context of a course, and so this was a course project, and I was like, this is a very interesting course project you did. I think other people should know about it, and so everyone's here. This is great. And so I'm telling you all about the course project they did, and I think it's germane to this.
Because presumably these problems wouldn't be too hard to do on paper.
Well, certainly these students don't know how to do it on paper. I didn't teach them that. Yeah, it's probably easier on paper. Yes. All right, so let's just wrap up here in good time. So look, we know some Copilot code is incorrect, right? Definitely does not pass test cases, definitely wrong. Something that I realized recently, which I don't know if you realized or not, is like, why do you have test cases for Dafny? And why you have test cases for Dafny is because it saves you time trying to prove things that you know are incorrect, right? And yeah, if you haven't thought about Dafny, then it's like, oh yeah, that's. So definitely there's some code that we shouldn't waste our time trying to prove because it's definitely wrong. It fails the test cases. Okay, so the things that pass the thing, that are test cases, we of course know that they're not definitely going to be correct, right? They might be wrong. Are they easy to verify or hard to verify? And so we know that some things are easy and some things are hard. I'm not saying tautologies, maybe I'm saying tautologies, but I think it's a useful tautology to state to put out there. And presumably it's easier to verify code that's designed for verification as opposed to code with Copilot. We didn't do that study. That would be also an interesting study to do. And so, of course, we're not verification experts. They took a course in verification of word term, and so they managed to do some things and not things. Other things, other people might do a better job than we did with this. I guess one of the review comments were like, well, what about more esoteric code or code that calls APIs or something like that? Like this is just leak code examples, right? And so I guess also talking about what James said, it's like, what if you had specific code? Would that be easier to verify or not? We don't know. We also cleverly dodged pointers and memory management by the Python code as opposed to like Java code with like references. Right, so we generated 6 code samples of Copilot. There were specifications and invariants and verified 4 of the 6. So TLDR, I guess we kind of knew this, but it's like, you know, it generates code quickly, but beware the generated code quality. And we know a bit more about some of the code we actually can prove, so it's not completely hopeless, but you're still, of course, playing with fire if you deploy Copilot code too broad. Maybe don't do that. Here's a gratuitous New Zealand photo from like 30 kilometers from here, O'Neill Bay. And if you're thinking about visiting around New Zealand, there's this webpage that I wrote with all the places I've been to in New Zealand. Thanks.
All right, we have some time for some questions. If there's questions online, raise your hand, but yeah, some from the room first.
Do you want to arbitrate or?
Oh yeah, go ahead.
So what if you just added a comment at the beginning of the prompt saying, write this code in a way that is easy to verify?
I should try that. That is, yeah, who knows, right? It might work. One easy trick gets you verifiable code.
Okay, so I had a question.
Sorry, yeah.
Yes. Did you think of like finding other Dafny code that was already verified and comparing that to what Copilot did? Like that may have helped you.
That might work, but we didn't try it.
Good.
Yeah.
So is Dafny old enough that Copilot is actually trying to some Dafny code?
I think the answer is yes. I think there might be some. Do you know, Dave? Yeah.
I haven't tried it in Copilot, but there is enough on GitHub that you think.
If you see someone raising a hand, let me know. Ilya?
Thank you. So Copilot can also generate tests. Have you considered using those in your specifications, at least post conditions?
So let's see. You generate tests from the.
You have a binary search. And then
Yep.
I want a test for binary search. Copilot gives it to you, so you don't actually have to write your post condition by hand. You can just get it from the test.
Well, so one thing I am actually legit interested in as a different research question is, can we come up with actual like post conditions from tests? But I don't think it's an easy problem if you just have, you know, if I give you 5, you give me 2, right? It's input output.
Yeah. So I have to say, I'm stealing this idea from Kevin Ellis' research. He's in Cornell, and he is ensuring at least some guarantees about Copilot generated code by asking Copilot to generate tests for this code as well, and then building some statistical theory out of it. So yeah, so tests are another form of specification in this case.
Yeah. Yeah.
I think there's some interesting follow-on work we can do here. So I was playing with ChatGPT this morning, and you can definitely give it some Python code and say, give me a for logic spec for this code. And give you a for logic spec and say, what do you reckon is the loop invariant here? And do a guess of the loop invariant, right? So I reckon.
Pardon me while my head explodes. That sounds totally legit. Yeah. That would be super interesting. It's like, is it? My guess, and it's just a guess, is that it wouldn't give you necessarily correct loop invariants, but who knows?
The one example I gave you gave a wrong invariant. Yes, just one test.
But it gives you things that look like proper invariants, right? But then, is it actually correct? No.
And it gave why I thought it was correct. That's the three properties you want to check for your invariant. That's in natural language, so it was convinced.
Yeah. It looks right. It's kind of like you're kind of talking to someone who doesn't really know what they're saying.
But you could imagine in a conversation with you were having to verify the program, that could be super useful to give you a starting point.
Yeah.
And then you say, well, actually, it doesn't work here. Let's iterate. I'm sure you could get your invariance a hell of a lot quicker that way than just staring at the Dafny timeout and going.
Yeah, like people hate blank slates, right? And so, I think that if you, the thing is, the neat thing about Dafny, right, is that it's not going to let you get away with bullshit, right?
Right.
And so even if you're talking to someone pretty smart, sometimes you'll get bullshit past them, and Dafny won't let you do that.
Let's see, I think the next question was here.
So I'm not sure how well this would work on the examples you have, but like this was looking, I guess, at like deductive verification, like running the proofs by hand and then checking them. But there's some tools that try to like automatically verify programs, and then if it fails, it will try to give you a counter example back. So do you think that might help with figuring out if any of those examples incorrect? Like you weren't able to verify by hand? Because it talks about that the code might be so complicated that even these verifiers can't deal with it. So
I think it would be used. I think Dafny doesn't tell you because it just times out, right? But if you have other tools and it's like verification fails because of X, then that would be obviously more to work with.
So like some tools like actually try to give you like traces to the program that do verify something. I mean, violate something.
Yeah.
Yeah.
So I just wanted to add on to that previous comment. I guess I don't really have a question, but it's one of the difficulties in verifying actual code is you don't usually have like a formal spec. That's usually one of the more difficult parts. So I was wondering, if either you could use a tool like GPT or Copilot to generate a spec from code, maybe the code that it generated itself, or if maybe it would be more effective if you provided the spec along with, say, the signature, if that would help make it pass more test cases or something.
Yeah. The thing is, like, I don't really trust computers, right? And I don't know, there's a whole discussion to have here. Like, you have this spec, it's computer generated. Is it the right spec? Maybe. Do you trust it? I wouldn't trust it. But is it better than no spec? Yes.
I guess on the other hand, though, you have the problem with like a human motor spec. Can you trust that either?
No, it's totally legit question.
Not that I'm regret.
All right, Cyrus.
So the examples you gave seem to be kind of like common examples. Like I imagine there are multiple copies of just those exact solutions on GitHub already.
Yeah.
Did you actually go like look to see if the code generated was just a copy paste of something from an existing repo, or is it novel?
I didn't do that.
Okay.
I don't think we picked one.
That's a curious question.
That is, but I mean, like that would be kind of disappointing, right? That would be, it's possible.
What I would expect it's doing in a sense, right? Like if it can find exactly def max heapify in one of the repos that it's learned from.
Right. My point is that it's disappointing that it's learning from the battery example. It's like, you should not be like that. You should be like your brother, right? It's like you're learning from the wrong example.
All right, we should move on to the next talk. Thank you.